Yes, recording. So welcome back, everyone. So the second talk of the day will be given by Matt Conder from University of Auckland. And he'll be talking about discrete two-generator subgroups of PSL2 over the p-adic rationals.
Thanks very much, Mikhail. Thanks for the introduction and the invitation to speak. So yeah, as you said, I'm Matt. I'm currently a postdoc at the University of Auckland. And so in this talk, I'll be talking about ongoing joint work with my colleague Jeroen. So I say ongoing in that we're fairly confident that we've finished a classification of all discrete two-generator subgroups of PSL2 over the p-adics, but we're just sort of finalizing final details and final checks and things like that. But I'll talk to you about what we've done so far. Okay. So a motivating question, sort of why are we interested in these discrete subgroups? So a motivating question is given two elements of the projective special linear group PSL2 over the complex numbers. Do these two elements generate a discrete group? And so discrete subgroups of PSL2C are known as Kleinian groups, and they're very well studied and of wide interest to people in geometry and topology because there's strong connections to three-manifold theory. And so this is already quite an interesting question. Lots of people are interested in it. Just a quick note that here by discrete, I mean you take SL2C, your 2x2 matrices of determinant 1 with complex entries. You embed that into C4 sort of in terms of coordinates, and you say that such a subgroup of PSL2C is discrete if the corresponding topology you inherit from C4, and then by taking the quotient topology is the discrete topology. Or equivalently, if you have a sequence of elements converging to the identity, then it has to be eventually constant. Okay, so a quick example of a two-generated subgroup of PSL2C. So here I'm giving you matrices, but you can just think of the sort of equivalence class of these matrices in PSL2C. And so we look at the subgroup generated by these two matrices. Clearly this will be discrete if this sort of variable rho is a Gaussian integer. And then also it turns out that this subgroup G rho is both discrete and free when rho lies in this subset of the complex plane called the Riley slice. And so this has also been studied by lots of people interested in Kleinian groups. There's a picture here which I've taken from a recent paper of Jeroen and some of his collaborators. So the Riley slice is everything, the sort of exterior part in this picture here. And so any complex number rho which is in this Riley slice gives you a two-generator subgroup of PSL2C, which is both discrete and free. Okay, so this is sort of some of the motivation for why we're interested in discrete two-generator subgroups. That's Kleinian groups in general. Sort of answering this question is very hard. So this is just one specific example, and it's known sort of what's going on in the exterior of this picture in the Riley slice, but in the interior, it's still a little bit of a mystery. If we restrict to the real numbers, so subgroups of PSL2R, discrete subgroups of PSL2R are known as Fuchsian groups. In this case, it's a bit easier to determine discreteness, and there's a complete classification which has been given from work of lots of people. And so I named Rosenberger here because he gave a sort of summary of everyone else's work. Purzitsky was one of the main contributors towards this classification, but essentially between a lot of people, you take any discrete two-generator subgroup of PSL2R, and you can, it has to be one of the following isomorphism types. So it could either be cyclic, so that's either finite cyclic or infinite cyclic, or it could be an infinite dihedral group. These groups are called elementary subgroups of PSL2R, and the rest are non-elementary. Another option is that you could have a discrete and free group. So it could be a group isomorphic to the free group of rank 2 that's also discrete. You could have a free product of two finite cyclic groups. You could have a free product of a finite cyclic group in the integers. You could be this is a hyperbolic triangle group. So it can be geometrically realized in terms of reflections across a triangulation of the hyperbolic plane. A group of this type, so two generators and some finite order commutator, and then a group with this presentation. So the reason I'm stating this theorem is that the main theorem Jeroen and I have proved is sort of an analog of this in the p-adic setting. So if we take a discrete two generator subgroup of PSL2 over the p-adic numbers, we can give a finite list of isomorphism types of these groups. So very similar to this list. Not quite the same, but similar. Okay, I'll just point out here, so I didn't want to clutter the slides too much. So here, N and M are all positive integers, which are at least 2, and L as well. So a question, can we do a similar classification over other locally compact fields? So the class of local fields or locally compact fields can be split into 2 subclasses. So you've got Archimedean local fields, which are either the real or the complex numbers. This question has been done over the real numbers here. Over the complex numbers, it's quite tricky. So what about the non-Archimedean local fields, such as the p-adic numbers? So on the next slide, I'll introduce the p-adic numbers and then continue. But does anyone have any questions at this point?
Well, yeah, I'm just curious whether all possible combinations of M, N, and L in general can appear, or whether it's just like certain happen.
That is a very good question. I'm not 100% certain, but I suspect that all possible combinations possibly can occur. I would need to double check that. Yeah.
Yeah, thank you.
Okay. So as I was saying, we're looking at answering this question of, can we classify the discrete two generator subgroups of PSL2 over a non-Archimedean local field? And I'll focus in on probably the most well-known example of this field, these types of fields, which are the p-adic numbers. So the p-adic numbers are an extension, or the completion of the rational numbers with respect to a specific absolute value. And so how you define this absolute value, you take a rational number x, you write it in the form p to the r times a over b, where p is your prime and a and b are not divisible by p. And the p-adic valuation of this rational number x is this integer r, which is the power of p in this factorization. And then the absolute value, which you complete the rationals with respect to, you take p to the power of minus the valuation. So that gives you the p-adic numbers. Every non-Archimedean local field is isomorphic to either a finite extension of the p-adic numbers or the field of formal Laurent series over a finite field. So the p-adic numbers are very, very central in this class of fields. And the reason why we're particularly interested here is that if you take a group PSL2QP or over any non-Archimedean local field, and the whole point of these talks today is we're interested in Bruhat-Tits trees. These are a structure on which these groups act by isometries. And so you can determine quite a lot of interesting information about these groups by studying the geometry of the action on this tree. And so here's a picture of the is very similar to the picture that Claudio had. This is the three regular Bruhat-Tits tree corresponding to PSL2 over the two adics, or any non-Archimedean local field with residue field isomorphic to F2. And throughout, I'll denote the tree corresponding to the p-adics for fixed prime p by TP. Okay. So a bit of background about groups acting by isometries on trees. So here by a tree, I'm going to restrict for this talk just to simplicial trees. But a lot of what I talk about in some cases can be generalized to R trees and lambda trees, or whatever type of tree you're interested in. But if I say tree, I'm going to just mean a simplicial tree. So if you have an isometry of a tree, you can define its translation length, which is essentially the minimum distance that this isometry moves any vertex of the tree. We're also going to assume that by subdividing the tree, if need be, that every isometry acts without inverting edges. And by making that assumption, we can classify isometries as either elliptic or hyperbolic. So an elliptic isometry fixes a point on the tree. And throughout this talk, we'll use fix of G to denote the fixed point set of this isometry, so the subtree which is fixed by G. The other class are hyperbolic isometries, and they translate along an axis or a bi-infinite path in the tree. And we'll use xg to denote this axis. And just a quick proposition that if you're given an element of PSL2 QP or a matrix representing such an element, you can compute the translation length specifically depending on the valuation of the trace as so. Okay. So this theorem is not a classification result, but it's sort of the key underlying theorem that we will use to exhibit our classification. And so in general, if you just take any two generator group acting by isometries on a tree, and if you've been to any of my other talks, you'll know that in my PhD work, I took such a two generator group and showed that you can perform a sequence of translation length minimizing Nielsen transformations to get to a sort of a minimal generating pair. And so if you do this finite process, you end up with a minimal generating pair. And what Jeroen and I have shown is that there's sort of four possible cases that you can be in terms of the structure of the group once you're at this minimal generating pair. So we'll call these minimal generators A and B. So if A and B are both elliptic and they fix a common point on the tree, then clearly your whole group fixes a vertex of the tree. So this is sort of the first option. The second option is that your group is a free product of the group generated by A and the group generated by B. And this can occur if A and B are elliptic with disjoint fixed point sets, or A is elliptic, B is hyperbolic, and the intersection between the fixed point set of A and the axis of B is sort of sufficiently small or empty. Or the third option is that the A and B are both hyperbolic and their axes overlap, or either are disjoint or they overlap in a sort of sufficiently small way. And the point of this translation length minimizing procedure is that one of the sort of possibilities missing from this classification is that you have two hyperbolic elements with a large overlap in terms of their axes. And what this translation length minimizing procedure does is reduces that overlap until you're in one of these other cases. Okay, so I'll point out, so this first class it's pretty clear to see this second class, this free product thing, this is sort of known based on work of Kapovich and Weidmann and Culler and Morgan. This third class is also fairly straightforward to sort of work out. So what have we got here? Two elliptics with not disjoint fixed point sets, or they have a disjoint fixed point set, or two hyperbolics with a small overlap. And I said if they've got a large overlap, you can reduce it to one of the other ones. So we're reduced to the case where A is elliptic and B is hyperbolic. The intersection between them can't be small, so it's either infinite or sort of finite and large, and that'll be these two remaining cases. If it's infinite, it's fairly easy to construct a sequence of conjugates of A by powers of B, and either this gives a sort of infinite set of distinct elements all fixing some particular vertex, which means your group has an infinite vertex stabilizer, or at some point two of those conjugates coincide, so you get that A commutes with the power of B. So then this fourth case is our sort of tricky case. And I gave a talk a few months ago at the matrix meeting. I think that was in November or December, I can't quite remember. And this was sort of the sticking point. Jeroen and I were quite stuck on trying to classify the groups generated by A and B, where A was elliptic, B was hyperbolic, and the intersection between the fixed point set of A and the axis of B was a large finite path. So here we're going to say the length of this path is delta, and it's at least the translation length of B. The terminal vertex is Y. So here by terminal, I mean with respect to the direction of translation of B along its axis. And throughout, we'll focus on the subgroup G0. So it's generated by conjugates of A by powers of B up to the kth power of B, where K is the floor of the length of this path divided by the translation length of B. And so in this weird, tricky case, we've got these three specific subcases, and this seems, I don't know, this is quite technical for a classification, but it will turn out these three things are sort of exactly what we need to complete our classification. So the first option is that G is an H and N extension of G0 with stable letter B. And you can show that G0 is precisely the vertex stabilizer in G of this terminal vertex Y. And so how we showed this was by using a version of Klein's combination theorem given in Maskit's book on Kleinian groups. And then these other two conditions are basically what happens if any of the combinatorial conditions for Klein's combination theorem fails. There's two possibilities for it to fail in such a situation, and this is sort of one of them, and this is the other. So the first possibility where it fails is that G0 contains some subgroup H, which fixes at least two vertices and properly contains sort of a version of G0 minus the generator A, or the overlap is precisely a multiple of the translation length of B, and there's an element in your group G0 that kind of, it takes if you look at Y, which is your terminal vertex, you apply B to it to shift it away from the overlap, and then G sort of reflects in Y to the opposite vertex. So we've got four possibilities here. Three of them are fairly straightforward. The fourth one is the tricky one. And essentially it's saying either you're an H and N extension or some kind of difficult stuff happens. And so for the rest of the talk, I'll sort of elaborate on how we can rule out some of this difficult stuff and reduce it to something a bit simpler. Okay, I'll pause for a second there if anyone has any questions. Okay. So yeah, this fourth part is quite specific for what we need it for, but the theorem overall is very general. So you'll notice nothing in this statement has anything to do with PSL2 over the p-adics. It holds for any two generated group acting by isometries on a tree. So perhaps this might be useful for someone else interested in such groups. Okay, so if we think back to what's the point of all this, we want to classify two generator subgroups of PSL2 QP, which are discrete. So we need a method of determining when such a group is discrete. There's a paper of Cato from 2005 that gives this exact lemma. It's probably been proven by other people, or it's fairly well known. But if you do have a subgroup of PSL2 over the p-adics, if it's discrete, then every vertex stabilizer in your group is finite. And this follows essentially because the Bruhat-Tits tree at axon is locally finite. Every vertex has a finite number of neighbors. So if you had an infinite vertex stabilizer, then you can find an infinite sequence of distinct non-identity elements that converges to the identity, which violates discreteness. On the other hand, if you do have a finite vertex stabilizer, then you look at any sequence of elements converging to the identity. Eventually, all the elements in the sequence will lie in this stabilizer, but because it's finite, your sequence has to be eventually constant. So G is discrete. So we've got these conditions for discreteness, and we'll apply these to types 1 to 3 from our structure theorem on the previous slide. So the first case of the key theorem was that the whole group G fixes a vertex of the tree. That means that G is the stabilizer of some vertex. And so if it is discrete, then the stabilizer has to be finite, therefore G has to be finite. And clearly if G is finite, then it's discrete as well. So in case 1, or a group of type 1, you're discrete if and only if you're finite. And the finite subgroups of PSL2 QP are well known. So you're either cyclic dihedral, A4, S4, or A5. And this follows by a fairly straightforward argument that if you have a finite subgroup of PSL2 QP, you can argue that it's isomorphic to a finite subgroup of PSL over the finite field of order P. And it's well known that those subgroups can only be one of the following. Okay, so that's our groups of our first type. They're finite and one of these 5 options. Second case, we had the free product. By Cato's result, you can't have any infinite order elliptic elements. If you had an isometry or an element of PSL2 QP, which was elliptic, so it fixes a point, basically because stabilizers are finite, you can't have that elliptic element being infinite order. So if you do have a free product of this form, then A and B are either both hyperbolic or both elliptic of finite order, or one of them is elliptic of finite order and the other is hyperbolic. So you get either a free group of rank 2, a free product of finite cyclic and Z, or a free product of 2 finite cyclic groups.
Excuse me a minute, Matt, doesn't that give you the theorem, then give you a bound on M and N?
Yes, yeah, it does. So yeah, I'll say a disclaimer that to sort of not overload the slides, although they already are quite dense, I've sort of removed all bounds and everything on M and N. So in our classification, there are bounds on M and N, but also there are relations between M and N and P. So there are certain congruence classes of P mod N or M for which these groups can occur. But for simplification, I'm just going to ignore that in this talk. but yeah, you're right. These cyclic and dihedral groups can't be too big. Okay. So the third option was we had an elliptic generator and a hyperbolic generator with the overlap between the fixed point set of A and the axis of the hyperbolic one being infinite. It contained a geodesic ray. And in this case, either A commuted with the power of B or you have an infinite vertex stabilizer. Clearly, the second case, you can't get a discrete group. So A commutes with the power of B, but as we're dealing with matrices, you can show that that actually means A commutes with B, and then you end up getting a direct product. So of the form finite cyclic cross Z, where here we're going to allow for the case that this could be the trivial group as well. So perhaps you do this reduction, you get your generators, well, basically your two generator group could reduce to a one generator group, which could be the integers generated by a single hyperbolic element. Okay, so those are sort of the easy cases. So what about the harder case? So this is just a recap in terms of what groups of type 4 are like. They're generated by an elliptic element A and a hyperbolic element B with such that the fixed point set and the axis have a large overlap. Y is the terminal vertex of this path of overlap, and we have this group G0. And these are our options. So I'm going to outline the sort of plan of attack for the rest of the talk and how we end up proving our classification. So first of all, you can observe that, so G0, because of how we've defined K, every generator of G0 fixes this terminal vertex Y. And so because G0 fixes some vertex Y, the stabilizer of Y contains G0. And in particular, G0 has to be finite, otherwise you're not going to get a discrete group. So to sort of tackle this problem situation, we're first going to list all the possible isomorphism types of G0. So we know that it's finite, so it has to be either cyclic dihedral A4, S4, A5. We're going to be able to rule some of those out and also show that up here, this length of this path of overlap could be arbitrarily large, but still finite. We're going to show that, in fact, it has to exactly equal the translation length. Then what we're going to do is show that this, if G is discrete, then the second case doesn't actually occur whatsoever. So you can rule that out entirely. And so then what you're left with is this H&N extension case, or this sort of case 3 where K is equal to 1. You know that the overlap is precisely equal to the translation length of the hyperbolic element. And we're going to show that this condition here is equivalent to the existence of a reflection in the axis of B about this terminal vertex Y, in which case G has the structure of an amalgamated free product. So essentially, if you're a group of type 4, we prove that either you're an H&N extension or an amalgamated free product. Okay. Any questions about that? Right. So before we sort of get into the detail of that, I'll outline some important results that'll help us sort of get to this classification. So the first is a result of Lubotsky and Weigel from 1999, which gives a sort of a short list of possible fixed point sets for finite order elliptic elements in PSL2 QP. So if you have any finite order elliptic element, its fixed point set either consists of two adjacent vertices, in which case not only does your your element has to have order 2 or 3, but it also has to have order p, where p is the prime for which you're defining the p-adic numbers. So this is quite limited, and it can only happen when you're working over Q2 or Q3. So these are sort of the two main other cases. The fixed point set is either a single vertex or a bi-infinite ray. And I sort of alluded to this before, you get these congruence conditions. And apart from this theorem, I'm going to ignore the congruence conditions in this talk. But if you want to see all the sort of detailed congruence conditions, they'll be in the paper when we finally get around to finishing it off. Okay, so the point here is that essentially, if you assume p is not 2 or 3, or sort of for a very, if you exclude a very limited number of cases, a fixed point set is always a single vertex or a bi-infinite ray. And so because these are grouped based on congruence classes, you can show that elements, finite order elliptic elements of PSL2 QP have what we call the fixed point power property. So if you have a finite order elliptic element A, its fixed point set coincides with the fixed point set of all non-trivial powers of A. Basically, because if something is fixed by A, then it's fixed by any power of A. So fix A is a subset of fix A to the I. And then you can show that those two fixed point sets have to lie in the same, you have to have the same congruence condition going on. So they have to be of the same type. They're either both a single vertex or both a bi-infinite ray, or both a pair of adjacent vertices. And so they have to be exactly the same. So I put this in red because we're going to use this property again and again and again throughout our proof. And in particular, we can use it to show this result, that if you have and this will be how we rule out this case II, where I had some random subgroup fixing at least 2 vertices. If a finite subgroup of PSL2 QP fixes at least 2 vertices of the Bruhat-Tits tree, then it's either cyclic or the Klein-4 group. So you can be quite restrictive based on that. How this proof works is that essentially we know already that a finite subgroup has to be either cyclic dihedral A4, S4, or A5. And you work through each case and use the fixed point power property to find 2 elements which have the same fixed point set, but they don't commute. And the 2 elements that have the same fixed point set, that fixed point set is a bi-infinite ray. So if they have the same fixed point set, they're fixing the same 2 points on the boundary of the tree. And so by conjugation, you can assume that the representative matrices are both diagonal, in which case they should commute, but they don't. So you get a contradiction. So in all the possible finite subgroups, you can get a contradiction in every case, unless your group is cyclic or the Klein-4 group. Okay. So now going back to our sort of problem case. So we've got an elliptic element A and a hyperbolic element B. The fixed point set of A intersects the axis of B in a large finite path. Because we know now that fix A is either a single vertex, a pair of adjacent vertices, or a bi-infinite ray, because the translation length of any hyperbolic element has to be at least 2, you know immediately that the fixed point set of A is a bi-infinite ray. And so if we go back to here, you immediately get this congruence condition. But as I said, for the purposes of this talk, I'll ignore the details of the congruence relations. Okay, so we know that fix A is a bi-infinite ray. And as I said, we can argue that this finite path, although currently all we know about it is that it could be finite, but as long as you want, will show that in fact the length has to exactly equal the translation length of B. And that follows because if it's strictly larger than the translation length of B, then your group G0 fixes at least 2 vertices. So by the previous result, it's either cyclic or Klein-4. In particular, it's abelian, which says that A and B inverse commute, but that only happens if the 2 fixed point sets are the same. Again, remembering they're bi-infinite rays, so by conjugation, you can assume they're both diagonal matrices, both represented by diagonal matrices. And this is a contradiction. You can look at, instead of the terminal vertex of this path, you could look at the initial vertex of this path. And it's fixed by A, but it's not fixed by B inverse. So these fixed point sets are not the same. So this length delta has to equal the translation length of B. Moreover, if G0 is cyclic or a dihedral group of even type, so the group D2n of order 4n for some positive integer n, then a similar argument and using the fixed point power property for the dihedral case gives a contradiction. So summarizing what this means, we're in this strange setting, and we know that G0 has to be finite if our group is discrete. We've shown now that this overlap between the fixed point axis of A and the translation axis of B is precisely equal to the translation length of B, but moreover, our group G0 is either dihedral of odd type A4, S4, A5, as it can't be cyclic, or dihedral of even type. And so in particular, looking at all these possibilities, if this sort of case II thing occurred, where G0 contains a subgroup fixing at least 2 vertices and properly containing a sort of a version of G0 with 1 less generator, then this means that this subgroup H has to either be cyclic or Klein-4 because it fixes at least 2 vertices, properly contains A, and so by looking at possible generating sets for G0 in each of these 4 cases, you can basically rule out that this subgroup H can ever exist. And so now we're down to this dichotomy where either our group is an H and N extension, or there's some element which is starting to look like it's going to be a reflection about Y in the axis of B. And so on the next slide, we'll show that in fact this condition becomes equivalent to the fact that there's a reflection in the axis of B about this terminal vertex Y. Okay. So yes, ignoring the H and N extension case, suppose, so we've now reduced to this case, A is elliptic, its fixed point axis intersects the translation axis of the hyperbolic element B in a path of exactly the length of the translation length of B. Y is the terminal vertex of this path. We have a finite subgroup G0, and this condition III, there exists an element of G0 taking By to be inverse Y. So first of all, using the fixed point power property, you can show that every element of the form B times some power of A times G has order 2. And using that, you can write B inverse in terms of A and G, and you can deduce that G0 is actually generated by A and this element G. And then by looking through the possibilities for G0 on a computer program like GAP or Magma, you can check that some element of the form AIG has order 2. And basically, well, we need a G which does this, maps By to B inverse Y. But B inverse Y is fixed by A. So any element of this form also maps By to B inverse Y. And doing the search on GAP or Magma, some element of this form always, well, yeah, it's always the case that some element of this form has order 2. And so because these elements do the same thing we want, we can assume that G has order 2, G is an involution. Again, using the fixed point power property, you can show that GB is an involution. And then by induction, this tells you that G is a reflection in the axis of B about this terminal vertex Y. And conversely, if you had a reflection in the axis of B about the terminal vertex Y, then clearly this condition holds. So the point is, if you're in this setup and you have such a reflection, then you can apply these versions of Klein combination theorems given in Maskit's book on Kleinian groups. There's one for amalgamated free products, there's one for H&N extensions, which we've already used. There's also one for amalgamated free products. And you can use this once you know there's such a reflection existing to show that G is the amalgamated free product of G naught and this group here over the cyclic subgroup generated by A. And moreover, you can show that this group on the right here is dihedral of order M, where M is the order of A. So you get something like G naught star DM amalgamated over a cyclic group of order M. And you also get this stabilizer condition. So the point of all this is that if G naught is finite and there is this reflection that exists, then G naught has to be the stabilizer of this terminal vertex Y. And moreover, there's only 5 possible isomorphism types. So essentially, because G naught is generated by 2 elements of the same order, if it was dihedral, then the element A, or the order of these elements has to be 2. And so this is the only possibility that you can get. Remember, G naught has to be a dihedral group of odd type, and it's generated by 2 involutions. So this will be D2 amalgamated over C2. And similarly for these other options, A4 can only be generated by 2 elements of order 3. S4, A has to have order 4, and A5, A has to have order 3 or 5. And then moreover, so this is, if there is a reflection, then you get one of these amalgamated free products. If G naught is isomorphic to S4 or A5, then you can show using trace arguments that there always exists such a reflection. And so basically the H&N extension case can't occur, and you always get one of these amalgamated free products. Okay, so that basically completes the proof, which means we can now give our final classification. So if we take G, a discrete 2-generator subgroup of PSL2 over the p-adics, either it's finite, so this was when it's generated by 2 elliptic elements fixing the same vertex, and then we know it's either cyclic dihedral A4, S4, or A5, where again these are of bounded order, but I'm ignoring the sort of conditions on that for now. It could be discrete and free of rank 2, so that's generated by 2 hyperbolic elements with small overlap between their axes. Could be the free product of 2 finite cyclic groups, so this is generated by 2 finite order elliptics with disjoint fixed point sets. Could be the free product of a finite cyclic group in the integers, so this is a finite order elliptic element, and a hyperbolic element is the generating set with the overlap between the fixed point set and the axis being small. You can get a direct product of a finite cyclic group in the integers, or just the integers themselves. And this arises when you've got sort of an infinite overlap between the fixed point set of your elliptic generator and the hyperbolic one. Or these 2 remaining cases. So this was problem case 4, groups of type 4. Either they're an H&N extension of G naught, this group G naught, or they're an amalgamated free product because this reflection element existed, and we showed that this reflection element always exists if you're S4 or A5, and that your group G naught is never dihedral of even type or cyclic. So either you're an H&N extension of an odd type dihedral group or of A4, or you're one of these 5 amalgamated free products. And the way we've constructed this, there's also an algorithm which we're yet to implement, but we know that such an algorithm does exist, which if you give us a 2-generated subgroup of PSL2 QP, we can decide after finitely many steps whether or not it's discrete, and moreover, we can tell you which of these classes the group lies in. So this answers, well, in our case, we can answer the question that was asked at the start of the talk. Can these always occur? And so, as I mentioned, I've ignored some sort of conditions on what M and N can be, but under these conditions, all of these classes do occur. And so we have examples for each of them, and I'll give 2 specific examples. So one of them, for instance, you could look at matrices in SL2 QP, representing elements A and B in PSL2, with these, using these matrices. So this one here is elliptic, and T can be chosen to be whatever you want, so that A has order n for some n under some conditions between n and P. And this element over here is hyperbolic, and it's got translation length 2. And you can show that no matter what T is, these 2 elements are always, well, so long as T is chosen so that A is elliptic of order n, the fixed point set of A and the axis of this hyperbolic element B are disjoint, and so together they generate a discrete group, which is a free product of a finite cyclic group of order n and the integers. And these are the types of matrices we use to generate our H&N extensions and amalgamated free products. So this is quite complicated to sort of go into the details of, but essentially using a bunch of trace identities and Hensel's lemma, you can show that A and T can be p-adic numbers specifically chosen, so that these 2 elements, this is A, so this will be elliptic of some specified finite order. This is a hyperbolic element of translation length 2. You can find p-adic numbers A and T such that these elements generate any of the H&N extensions or amalgamated free products that I listed on the previous slide. Okay, so then finally, where do we go from here? So one of the current things we're trying to work on is generalizing this from the p-adic numbers to other non-Archimedean local fields. And it turns out that if you have a 2-generator subgroup of PSL2K, where K is a non-Archimedean local field with residue field of characteristic P, and it doesn't contain any order P elements, then we get this exact same classification. And so an example of such groups are co-compact lattices in PSL2 over the positive characteristic non-Archimedean local fields. And the point here is that if they do have elements of order P, then your fixed point sets are no longer just sort of vertices or a pair of vertices or an axis. They are sort of versions of those with an additional radius component. So you could have sort of a thick band in the tree. So you've got a bi-infinite path and then some radius components, so it's sort of a thickened band, or you could have a ball of positive radius. And that messes up our fixed point power property theorem, which underpins a lot of our results. So if there are elements of order P, what do we do? Not too clear in that respect yet. So this is, as I said, a possibility for future work. Also, so going back to the Fuchsian group case, there was a classification of all 2-generator Fuchsian groups. and Kirschner and Ruther used this classification to solve the constructor membership problem for such groups. So given some element of PSL2R and a two-generator Fuchsian group, how do you tell if that random element is a member of this Fuchsian group? And if it is, how do you exhibit it as a word in terms of the generators of this Fuchsian group? So can we mimic these methods in our case to solve the constructor membership problem for discrete two-generator subgroups of PSL2 over the p-adics? So we think it's possible. We haven't had the time to sort of look at it yet, but interesting question nonetheless. And then finally, Van der Put and Voskuil give a list of all possible amalgamated free products which can arise from discrete finitely generated subgroups of PSL2K for any non-Archimedean local field K. And so in particular, our amalgamated free products appear in this list. But this perhaps gives us some hope, because this is finitely generated subgroups, perhaps gives us some hope that it may be possible to classify discrete subgroups of PSL2QP generated by 3 or maybe more elements. It's probably a bit ambitious to think this might be possible, but I don't know, something we're interested in looking into anyway. Right, so I'll end it there. Thanks very much for listening.
Right. Well, thanks for the talk, Matt. Do we have any questions?
Yes, I have a question here.
Yeah,
excuse
Claudio.
me, Matt.
Yeah.
Firstly, nice talk.
Thanks.
I have a question about your exposition. Do you know what happened if we change the group PSL2 by something like SU3 or something like this? This is the specially unitary group of some quadratic Hermitian form defined on the space K3. Since here we have since SU3 has on one hand a copy of SL2, but on the other hand, it can be embedded on SL3. So we have the interaction of two groups in some sense. So I think that it can be interesting to regard.
Yeah, no, that's a very interesting question. I know that, so this fixed point set classification has been done for GL2, but by restricting to SL2, we don't get this issue of sort of having balls of large radius or sort of thick bands in the tree or something like that. But yeah, maybe, as you say, if PSU2 is related to what are you saying, PSL3 or PSL2 as well, maybe we can abstract results to different settings. Yeah, that's interesting. Thanks, Claudio.
Any other questions?
Thank you very much.
Okay. Any other questions? Well, I have one question. So you mentioned that you have an algorithm. So I assume that algorithm must work over rationals, because you can't really give a p-adic number. But then I'm just wondering, like, how numerically stable it is, because when you start working with the rationals, the actual numerator and denominator, they can start blow up really fast as you are performing operations. So, like, for example, is that an issue, or is that just something that you don't take into consideration for your purposes of your talk?
We haven't implemented it yet, so that's
okay.
It's not an issue we've encountered yet, but I imagine it would become an issue. Yeah. So I think there would be, well, I need to think about it some more, I think, but I suspect if you start with reasonably nice rational matrices, the number of steps in the algorithm will be quite small and it won't blow up. You won't get these sort of problems as you said, but yeah, I suspect that would always be an issue that we'll have to figure out how to deal with once we start implementing the algorithm. Yeah.
Yeah, okay, thanks.
Thanks.
Matt, do you have, can you say how long before this preprint appears?
Well, this thing here that we've mentioned, we only just realized we could do this. So we'd basically finished it off for the p-adics and we're ready to submit. And then at the conference in Texas I went to 2 weeks ago, we were talking to Alex Lubotsky and realized that we could actually generalize it to this setting. So two generator subgroups of PSL2K without order P elements. And so at the moment we're working through our draft to sort of change everything around into this setting. But I expect probably in the next month or so, we'll put a preprint on archive, I would say.
Okay. And this extension could apply to some finite extensions of the p-adics as well as to the function fields?
Yeah. So finite extensions that don't have order P elements, they can, which is an issue. And then, yeah, maybe this paper's already been sort of a long time in the works, and we keep pushing, putting it on archive because we keep realizing we can do more and more and more. And so maybe we can figure out a way of dealing with these order P elements, or maybe not. I don't know. It would be really nice if we could give a classification over any non-Archimedean local field altogether.
Yeah. Okay, thank you.
Okay, any further questions? Well, if not, let's thank Matt one more time. And I'll stop recording.
Thanks very much.